think of these achievements. So all this is not going to happen if we don't have a very advanced fabrication technology, especially for optical fibers. So without further ado, this is the presentation outline. For warm up, I will just briefly talk about the introduction on optical fibers, and then I will move to the responses of light and matter, responses, as we have low power or high power optical pulse, optical signals propagating inside the core of optical fibers. So depending on your intensity of your laser, whether you have a low power continuous lasers or you have short pulses from your picosecond or femtosecond lasers, you can have a very high peak power propagating inside the core of your optical fibers to give a nonlinear response inside from the core of optical fibers. And for the purpose of this talk, I think in Malaysia we are more familiar with the scattering-based nonlinear responses. For example, blue line and also Raman that been largely used for the fiber lasers technology and fabrications. But what I'm going to focus today is the ultra-fast responses that based on Kerr nonlinearity from the optical fibers. So these responses is ultra-fast, femtosecond or picosecond regime. So that's what I'm going to talk today. Next, we'll move to the advanced fiber fabrication methods, where I'm pretty much sure when we are talking about advanced fabrication methods, some of you guys have the pictures of photonic crystal fibers that have very interesting structures in the cross-section of the optical fibers that can have a hollow core, for example, that largely been taught for today's developments. So even though it's very interesting field to talk about, I will not going to focus on that part of the focus. I'm going to focus on still the very much step index design, similar to what we have in the current telecommunication standard silica-based telecommunication fiber optics, where we just change from the silica glass to novel materials, for example, silicon that can support nonlinear responses in the optical fibers. Next, we'll go into the post-processing of the optical fibers to change the geometry of the optical fibers from the cylindrical shape. We can change the longitudinal variation in the diameter, for example, by tapering, or we can reshape the tip of optical fibers to fabricate different structures that can enhance the properties from the optical fiber itself to give us more room to explore in terms of functionalities. Next, I'll move to the new recent interest in the group, especially from the fabrication of optical sensing devices from optical fibers, and how we can integrate whatever that we have learned in fiber-based development of optical sensor to the fabrication of nanostructured substrates for the purpose of optical sensing. So that's what I'm going to talk today, and I will conclude my presentation after that. So for warm-up, very familiar images, I guess, for everyone. We have the cross-section of optical fibers there. We have core and also cladding that made from silica material, silica glass, where the core and also cladding being doped with different materials so that we can increase the refractive index of the core while lower down the refractive index of the cladding to achieve this condition, so that the propagating light can be supported by total internal reflection in the core of optical fiber. That's the very basic, the step index design for our optical fibers, very standards. And of course, if we look back at 1980s on the first purpose of development of optical fibers, we we come to the knowledge that the optical fibers first development is for supporting our telecommunication systems. So back then up until now, we have like into 2020 itself, we have 2 millions of kilometers of optical fibers being laid down in the transoceanic fiber optic cables to connect us in the telecommunications, fiber-based telecommunication globally. And this involved the fabrication of billions of kilometers of optical fibers since then to support all of these development, and the number of fiber optic cables that going to be laid down is of course going to be increased due to demands of data and internet services. And we see the needs for fabrication of optical fibers will not going to slow down, especially at this era of technology. And then we cannot forget that instead of just optical fiber for transoceanic cable, we have inland connections that uh, provide us a high-speed data from the fiber to the home, fiber to the premises, fiber to the office, so that we get a high speed data to our doorstep, steps to our office and so on. So even the wireless telecommunication nowadays, the even though we are all connected wireless, basically the backbone of all that wireless telecommunications is optical fibers, glass optical fibers. So we are all connected by the wired systems for achieving the wireless telecommunication. So that's the inland use of optical fibers, both to support our telecommunications. But what's beyond that, we saw from the past, I think, 10 years, the developments of different dope of optical fibers. For example, these rare earth dope optical fibers, erbium, for example, to support the developments of fiber lasers. Then and up until now, we have high power lasers that being used in industry to cut steels and so on. So apart from that, we also have optical fibers for the function of environmental monitoring. For example, this is for soil displacement, and for medical purpose, we also have optical fiber in the endoscopy techniques, where to help the medical imaging of the patient. So whether we realize or not, we have optical fiber laid down beside us, and optical fibers penetrating in every aspect of life, every aspect of technology, whether we realize or not. So apart from all of this, what else that we can do from the optical fibers? So now I'm going to be coming to the theory of the optical fibers, where whatever that I'm talking about today is largely coming from the books of Agrawal, Nonlinear Fiber Optics, where you can have detailed information from the book. So when we are talking about linear and nonlinear responses of light, as we have pulses or weak signal propagating in the optical fibers, is really depending on your intensity of light, whether you have lasers from the low power continuous laser, or you have high peak powers, femtosecond or picosecond lasers, photons that traveling inside the core. The response of the materials to all these photons is different. And to describe that, we can use the Taylor expansions of polarizations with respect of electric fields, where in this expansion, we can see that there are few important terms that we can try to understand. For example, we have chi1 here, that is the first order of linear susceptibilities, and we have chi2 and chi3 here, which are the second and third order nonlinear susceptibilities. And if you look into all these parameters, it's really related to the intensity of light, where the respect when you have a low power, uh, largely you have a linear propagations, and once you have a high power lasers or photons propagating from the pulse lasers, you can have a different nonlinear response in the core of optical fibers, which is this is very interesting because nonlinear interaction open up lots of opportunity, especially in the field of photonics. So let's just visit all these important equations, all these parameters for chi1. For example, chi1 is the linear response, okay, where there are few terms that are important. For example, this one is frequency dependent refractive index that arise from the real part of your chi1. And for the imaginary part of chi1, we have loss, which also depend on your frequency. So we're going to visit both of these right after this. But for nonlinear response, it's really depending on the material that you have as a core. For example, silica and silicon, for example, they are centrosymmetric molecules. Okay, they have that centrosymmetric inversion symmetric molecules. So the even order of nonlinear susceptibilities will be cancel out to left the third order of nonlinear susceptibilities has the lowest order nonlinear effect that we can obtain from that silica and also silicon optical fibers. And in describing the third order nonlinearities, all these effects largely being known as curl nonlinear effects, where the refractive index of the where the nonlinearity is coming from the nonlinear refractions, where is a function of curl nonlinear index and also the intensity of light. Okay, the curl nonlinear index here and 2 is really related to materials that you use. Okay, it's material dependent. And of course, the intensity of light is proportional to the power of light that you're injecting, the average power of it, and also the effective area from the core. The smaller the effective core, tighter the confinements, the high intensity of light, more nonlinearity can be obtained. And of course, when we start talking about nonlinear effects, we cannot run away from gamma, which is the nonlinear coefficient, where it's also related to curl nonlinear index and also effective index. So that's the basics understanding of what happens in the optical fibers when you have weak lasers or high peak power lasers from the pulses propagating inside the core. So now we're going to visit on what the important term in chi1, which is attenuation and also frequency dependent refractive index. For attenuations, of course, I think everyone knows for our telecommunication windows around 1.5 micron, the loss 0.2 dB per kilometers, very standard one, but has the advancing in the fabrication techniques, we can have these conventional silica optical fibers to have a loss lower than 0.5 dB per kilometers, for example, from the Corning, Newport, and also Sumitomo optical fibers, silica-based optical fibers. These are the major companies that produce the silica optical fibers for the research and also for the purpose of telecommunications. Next, the next term is on the frequency dependent of refractive index, and frequency dependent refractive index is nothing but the dispersion that happens inside the core of your optical fiber when you have the photons propagating. And to explain about the dispersion, we can view it as a Taylor series expansion of the propagation constant with respect to the central frequency, where in this equation we can have beta 1, for example, that related to the group velocity, uh, the velocity of the pulse envelope, for example, that propagating inside the core. And we also have beta 2 that correspond to group velocity dispersions. And then we have beta 3 and so on, which are the higher order dispersion terms. So if we refer to this figure that we have here, this is the profile of dispersion profile in silica-based optical fibers. So we can see D is the total dispersion. And if we look inside this graph, we have two different profiles, two different types of dispersion that affecting the total dispersion in the optical fiber. There are material dispersion and also the waveguide dispersions. So by tuning the material dispersion, which of course related to the materials, and by changing the waveguide dispersion, which is the changing the geometry of your waveguide, for example, you can shift the position of zero dispersion wavelength here. So for silica optical fibers, the zero dispersion wavelength is around 1.32 micron. So below the zero dispersion wavelength, you have anomalous dispersion regime, where this is a regime where all these nonlinear people likes to work with, because if you can balance the dispersions and the nonlinearity, you can have a solitonic pulse propagation inside the core of optical fibers. So, at the wavelength regime, for example, at 1.5 micron, right, at our telecommunication windows, we have at the positive value of beta 2. Okay, so this is a normal dispersion regime of optical fibers. Okay, so currently in our telecommunication window, we are working at the normal dispersion regime. So when we're talking about the material dispersions, of course, you can use the Selmayr equations to approximate the value of your material dispersion. So this is the refractive index profile, has a function of frequency or wavelength at 200 Kelvin. So the changes in the refractive index as you change the changes in the refractive index as a function of wavelength. So that's on linear response, attenuation and dispersions. But when we start moving on the nonlinear responses, it is very important to bear in mind that this linear response play a role in supporting the nonlinear response, because if we have high loss, high attenuation, you got not enough power to get the nonlinear effect. If you can balance or you can work in the anomalous dispersion regime, you can observe many interesting nonlinear phenomena inside the optical fiber. So all of these interaction is very integrated with each other. And when we move to the nonlinear response, of course, we are talking about the short pulses of light propagation inside the core. It can be from your femtosecond laser or picosecond lasers, where, as I told you before, the N2, which is the current nonlinear index, is material dependent, okay, and and is always good to explain the nonlinear response with the advancement in the fiber fabrication methods, where we can change the core of the fiber core materials to different type of materials besides silica. Okay, so this is a figure that tells us the magnitude of the nonlinear refractive index in different materials. At the highest value, we have germanium and also silicon, and then at the lowest materials, we have silica. So if we want to probe high nonlinearity from the optical fibers, we can use these highly nonlinear semiconductors materials. So I'm very lucky during the time when I did my PhD, I'm able to work with all these with silicon optical fibers, where these fibers is still maintaining the step index design, so that you can easily splice with the conventional silica optical fibers. And depending on the fabrication method that you use, whether you have high pressure chemical vapor deposition, or you use molten drawing techniques which work at different temperature regime, you can have a different phases of silicon crystallinity in your optical fibers. For example, these two is hydrogenated amorphous silicon fibers fabricated from high pressure CVD technique, where from this technique we can have core, small core around 6, okay, and also 2 micron in diameter. So this is the cross section of the core, very nicely filled to the round shape of core. And then for polysilicon fiber, for the molten core drawing technique, we can have a polysilicon fibers that have slightly larger core diameter around 10 micron. So this on the silicon optical fibers. Right. So when we talk about the propagation of short pulses, right, in the core of optical fibers, whether they are silicon or silica, for example, the equation that describes what's the term that play a role to their propagation can be explained by nonlinear Schrodinger equations, where when we wanted to view the propagation in silicon core optical fiber, we can use some approximation, and we call this generalized nonlinear Schrodinger equation. So this is a generalized nonlinear Schrodinger equation that can explain what happened to these short optical pulses when they're propagating inside the core of optical fibers. There are different terms that play a role during their propagation. We have dispersion term that related to beta 2, group velocity dispersion and intensity. We have, this is of envelope. And then we have nonlinear term, which of course related to the intensity of light, and also gamma, where gamma can be is given by this equation, where is a function of nonlinear index and effective index, and also beta TPA. Beta TPA is the 2 photon absorption that happen inside the silicon core, where it tells us about how this electron moving in the structures of silicon from conduction band to the valence band, and in order to jump from the conduction band to the valence band, they absorb 2 photons, and that can induce loss in the silicon optical fibers. So the next term is absorptions. Absorption can be linear or nonlinear in optical fibers, where the linear term, of course, for material attenuation, for example, but another term that related to free carrier absorptions, which is the absorption of photons to make interstates, interstate movement, the electron making, the free carrier making interstate movement inside the conduction band, for example, and they absorb additional photon for that, which can induce loss. And of course, the cross section of free carrier absorptions, okay, is depending on the free carrier density, and the rate of free carrier density is related to the free carrier lifetime inside silicon. And depending on the length of optical fibers that you use, different terms going to play a role. For example, for silicon optical fibers, because they have high nonlinearity, you only require a very short length of optical fiber to probe all these nonlinear effects. For example, the one that I use, the longest is like 5 millimeters. The shortest I've been working with around 1.5 millimeters. So it's very short length of optical fibers, and depending on the length, whether it's lower than the dispersion length or lower than nonlinear length, different terms going to be play a role during their propagation. So because of the length that I'm using is very small, less than the dispersion length, so we can cancel the dispersion term in generalized nonlinear Schrodinger equations to give nonlinear and absorption terms that affecting the propagation of pulses in the core of optical fibers. So that's on the basics of the how the equation that describe how these pulses traveling inside the core of high index, high nonlinear materials. Next, of course, when we receive the fibers, we need to do linear and nonlinear transmission characterizations, where when we have this short length of fibers, everything needs to be in the free space. You need to do laser alignments, you need to do a coupling of light to the core of optical fibers. So this is a free space arrangement to characterize both linear and nonlinear transmission properties from the optical fibers, where, as I tell you before, that for linear effect, everything can be from continuous lasers, 6 milliwatt of average power. But once we moving for the nonlinear, we can use a femtosecond lasers with 40 megahertz repetition rate to give peak powers around maximum around 450 watts. So that's what happened if you want to characterize or you want to probe nonlinear properties inside the optical fibers. And we use cutback method to get the value of nonlinear transmission, and to compare with silica optical fibers, the loss in the range of dB per kilometers. But for silicon optical fiber, at 1.5 micron, we have 0.9 dB per centimeters of loss. So because the fiber is very short, these values still well acceptable, and has been moved to mid-IR regime, the loss can be further low down as we pass the two-photon absorption regime, nonlinear absorption regime in the silicon core. So that's for hydrogen and amorphous silicon fiber, very good quality one. But what happened in polysilicon fibers? Polysilicon fibers, I guess when we learn about the solid state physics, right? We learn about all these polysilicon and amorphous materials. So polysilicon have lots of grain orientation, crystalline orientation in the structures. So all these orientations, okay, can induce absorption, can induce scattering of light. So usually we have a high linear loss in polysilicon optical fiber in the range of 20 dB, 10 dB per centimeter, a very high loss to limit the observation of nonlinear effects. So this is what we have observed in hydrogenated amorphous silicon core fiber. We can see the saturation when we injected high peak powers to the core and measure the output using the power meter. We saw a saturation due to two-photon absorptions, and then when we observe the spectral evolution on the OSA, we can see that the broadening of the pulse due to self-phase modulation at 326 watts. So this is the peak power from your pulse. So by fitting the result with the numerical simulation, we got important values that related to the nonlinear properties of the optical fibers. So that's what happens in hydrogen and amorphous silicon fibers. Because of the very high quality of optical fibers, we can probe different nonlinear interactions that can be used in for example, this two is for signal processing, all optical signal processing by using nonlinear effects of cross-phase modulation and cross-absorption modulation, where it used a pump probe experimental arrangement, where here we can see that the information that we have in the pulse pump, okay, like this, we can transfer the information to the weak continuous probe signal. So we can imprint whatever information that we have in the pump to the weak continuous signal. So this is what we call signal processing, which means we transfer the data that we have from one channel to one channel by using nonlinear optics. So what else that we can do besides all optical signal processing? We can have generations of new frequency to support the dense wavelength division multiplexing system by surface modulation. This is in 6 micron, this in 2 micron, where we can see reductions in the threshold to observe similar broadening. Okay, when we use a smaller core around 2 micron here, everything, the confinement is very tight, very high intensity, highly nonlinear materials, so that we can lower down the threshold for nonlinear observation. The same goes with the supercontinuous generation. This is beyond 2 micron at mid-IR regime. So we can see that lots more channels can be generated using hydrogenated amorphous silicon core fiber when we move to the mid-IR regime. So these are examples of nonlinear properties or effects that we can probe from the optical fiber, that we can obtain from silicon optical fibers. For example, for signal processing or generation of new frequency. But what happened to our polysilicon fibers, that low quality polysilicon fibers that have 10 dB per centimeter loss, 20 dB per centimeter loss? We are not able to see all this nonlinear interaction because of the high loss from the optical fiber. So what should we do? Then the idea of post-processing the optical fiber came to me, where here we can induce the longitudinal variation to the shape of cylindrical shape of optical fibers using the tapering method, where you can reduce the core size from 10 micron in diameter to around 1 micron in diameter. So when I measure the lowest tapering that I achieved is around 900 nanometers core size. So by doing so, because when we taper the optical fiber, we supply heat to the materials, you know, the core will slightly be molten again, and as we stretch out the optical fibers, we can rearrange the crystalline orientations of the silicon materials, so that we can improve the crystalline orientation until we can lower down the absorptions or attenuation from 20 to 10 dB per centimeter to 3.5 dB per centimeter regime value at 1.55 micron. So at this attenuation level, we can observe the nonlinear interactions. So these are the first demonstration of the nonlinear, current nonlinear refractive index-based responses in the core of polysilicon fibers, where when we fit the results, we can obtain the value of important parameters that related to the tapered optical fibers. So that we started to move from the cylindrical shape of the core to different geometry of optical fibers via post-processing. So what else that we can do via these post-processing techniques? So that's the idea, which means we can use post-processing, we can change the geometry. Can we change the geometry of optical fibers? In the same time, we want to lower down the threshold to observe all these nonlinear effects. Can we do that? So I think it's a very micro-resonator, whispering gallery mode micro-resonators is also a very famous structures in photonics, where these micro-resonator have a very small shape, a small size, uh, micron to nano size, and because of this small mode volume of that, okay, and then because we have all these structures that can confine light, okay, in that small mode volumes that have a very strong confinement, the light that being coupled into the structures can make thousands of uh, rotation, I can say, propagation inside the resonator. For example, this, what happens, how the lights really propagating close to the surface of the structure to give uh, what we call whispering gallery modes properties. So the thousand circulation of light here can produce a very intense light that can lower down the intensity, that can lower down the threshold for nonlinear effects. So that's the very basic understanding of microresonator and how we can transfer this knowledge to the silicon optical fiber. What can we do on silicon optical fiber? So these are among the resonators that I've fabricated. Uh, I etch out the silica cladding using wet etching techniques, and I also reshape the tip of polysilicon optical fibers by using high power CO2 lasers. So I can reshape the tip of optical fiber to have this cylindrical shape. And then I also use numerical simulation to view uh, the modes, the whispering gallery modes inside these structures. And then this is the characterizations of the resonators. When you have broad light source, a continuous PLS, you broad light source, you pump into you inject it into the tapered optical fibers, and with the phase matching, you are able to excite to achieve coupling of light into your resonators. So this is image of that. We have tapered optical fiber, we have resonator here, uh, uh, and then we can have coupling of light. And then the dips here is correspond to the whispering gallery modes, the modes that propagating inside your cavity. So the quality factors tell us how good uh, the lights circling around your cavities. So in cylindrical shape resonator, I can have around 12,000 of the Q factors. But once I started to introduce spherical shape, I got around 100,000 of quality factors. So they make 6,000 circulation inside the optical fibers, inside the resonator to give a very high intensity light inside the structures. So from that, we know that this structure can support very good light, okay, propagations. So can we observe nonlinear effects from all this? So this is what we call nonlinear shiftings in optical fiber in the resonators using a pump probe technique for both cylindrical and the cylindrical and spherical resonators, and we observe curve nonlinear shifting that can be used to demonstrate the optical signal processing from the structures of microresonators. So now, instead of requiring hundreds of watts of peak power to observe, uh, for example, nonlinear interactions for signal processing, we can have around less than picojoule of energy required to observe all these switch on and switch off conditions at picosecond time regime, and this is at femtosecond pound regime. Per femtosecond uh, femtoseconds modulation regime. Sorry about that. So by using all these small cavities, micron in size, you can lower down the threshold for nonlinearities so that you can obtain the signal processing at very low threshold at uh, picosecond and also femtosecond modulation. So this is a very ultra fast signal switching, which is very promising for all optical signal processing. So we have covered on the nonlinear effects. Oh, almost three. Nonlinear effects. How advance, we can adapt the advanced fabrication methods to incorporation of nonlinear index materials inside the core, and then we can put different nonlinear properties from the optical fibers, and we can also post-process the optical fibers to observe even more functionalities from optical fibers. So that's on the femtosecond regime, picosecond regime. Can we do something at the linear regime? And the answer is yes. By using the similar concept of what we have obtained from the previous experience, we can also post-process the silica-based optical fibers. We can taper it down. We can polish the structures to give us D-shaped optical fibers, to give us tapered optical fibers, where because of these small optical fibers, they have all these changes will change the way the light's propagating, and then now we have evanescent fields that guide it at the interface of the fibers and also the surroundings. And when we coat the surface with gold, we can excite the plasmonic resonance from the structures so that we can use them as plasmonic sensors, for example, for DNA detection. So this is a very recent results during the postdoc time at UPM for detection of leptospira DNA that cause leptospirosis disease. So this is the severity of the leptospirosis disease that can be fatal in humans. And then this is a little bit on the theoretical understanding about the plasmonic resonance, where we have a metal layers. When we are able to achieve a phase matching between the coming incident wave, the wave vectors of the incident wave to the plasmon in the materials, we can excite these electron oscillations that related to the plasmonic resonance inside the metal, and has the as the amplitude of this plasmonic modes is extended to surrounding. Anything that happen in the surrounding, we can observe on the changes on the properties of the plasmonic modes. So this is the phase matching conditions that need to be fulfilled in order to excite the metals and to excite the plasmonic modes. And then metal have a negative permittivity so that we can observe the plasmonic modes. So sensor configuration, as I explained, we can use D-shape, we can use tapered optical fiber, coat them with the gold, and then in order to achieve immobilization of probe DNA and also target DNA hybridization, we need to functionalize the goal layer using self-assembly method, where, for example, here by a self-assembly method, we have chemical functionalization group, which enable the immobilization of the probe by biomolecule probes. And once we introduce matching target, we can have hybridization on the surface of our sensors to get the shifting in the profile of the SPR for the purpose of sensing. So before we can move there, it's always good to start to experiment with the simulations. So I use finite element methods where I have developed model 12 micron in diameter tapered optical fibers coated with 50 nanometers layer of gold, and we have suitable boundary conditions, meshing the structures and the model, and you can see, you will be able to excite the plasmonic modes in the gold layer here. You can see here. So this is the optical modes that excite the plasmon in the metal. Okay. So, all right. Is it time? Very. All right. When we observe the profile, we can see that we have lots of electric field at the surrounding, so that this configuration is very suitable for the purpose of sensing development. And this is how I functionalize the surface of my goal with TOL and also NHS layer. And then this is how the experimental setup and the sequence of the DNA probe, target, and also non-complementary DNA. And then this is the results from the plasmonic resonance. This is what happened during the functionalization steps, and figure B and C to tell us about the shifting in the profile of XPR when we introduce different concentration of DNA from 0.1 femtomolar to 1 micromolar. And then when we plot the sensor response, they have a linear response with the sensitivity of 0.7 nanometer per log molar. And then the limit of detection around 0.1 femtomolar. And then this is the specificity specificity test using non-complementary DNA. So some are the analyzing using the SEM. This is the BEGO. This is POL layer. This is NHS layer, and this is the probe after the probe functionalization. And this is what happened after immobilization of the DNA. And then we can also use Raman spectroscopy to know the Raman vibration of this DNA. And then we saw these peaks that correspond to DNA vibrations on the sensor surface to indicate successful hybridization on our surface. So that's on sensors developments, how we can translate our knowledge from the optical fibers sensors can we do on the substrates. Okay, we use bulk thin layer 50 nanometers, but can we use nanostructures on metal now? To answer that is yes. We can use SIRS effect, surface enhanced Raman spectroscopy, with the help of photonic crystal structure. We have photonic crystal structures in butterfly, in environment. We have 3D arrangement on the geometry until you can obtain a band gap from the structures. And from the nature, we try to mimic the things by using chemistry developments. We have photonic crystals fabricated from polymers, and then we kind of immobilize nonlinear, immobilize nanoparticles, metal nanoparticles, whether gold or alloy, on the photonic crystals, so that when we able to match the band gap of the photonic crystals to the resonance of these nanoparticles, we can get enhanced surge interaction. So this is what we have obtained up until now. By varying the sphere diameters, we can get different photonic band gap properties, where we try to closely match with the Raman from the plasmonics from the alloy, so that when we have a close match from photonic band gap to the resonance at alloy, we hope to get a stronger surge interaction for the purpose of sensor developments. So that's everything from past couple of years up until now. So basically all of this is made possible because of these enhanced fabrication methods, post-processing the optical fibers. So there's lots of opportunity, very vast research that we can do. It's always enjoyable to work with all my colleagues, all my fellow friends, even my supervisors, my supervisors doing postdoc, and all my fellow friends, and also my students, to make this possible. I think that's all for me today. Thank you very much for lending me your ears for 1 hour. Thank you.
Okay, thank you so much, Dr. Fariza, for the very, very insightful talk and the very, very many equations. We have one question in the chat box. So it's from Ahmed Sabri. Assalamualaikum. Are you talking about when we increase the power of injected pulses, this will lead to go to the nonlinear characteristics for optical fiber?
Yes, for sure. Even when you use silica optical fibers, you can have all these nonlinear interaction, but you need a very long length of optical fibers, 8 kilometers, 15 kilometers. How many kilometers that we need? Long length of silica. If we don't have nonlinear fibers, right? We can put all this nonlinearity in silica optical fibers, because silica is low loss. And when we have a long length of optical fibers, the accumulative of the intensity, okay, so that you can still have nonlinear interaction from the optical fibers, but is more easier if we have high pulses, high laser pulses, so that we can reduce the length. And if you have a highly fiber optic, highly nonlinear fiber optic, we can even reduce the length. So depending on whatever that you have in the lab, if you have silica optical fibers, to observe all these non-linearities, you need a very high length. So if you have high nonlinear optical fibers, you just require a short length of fiber. So yes, the answer is yes. Another question, Nadiah?
All right, I think Dr. Yasmin has a question. Right?
Hi, Dr. Fariza. Okay, so my question is, first of all, thank you very much for the talk. I find it interesting when you showed that you couple tapered fiber with a micro resonator.
Yeah.
The slide that showed that. Do you, in elaborating any application from that perhaps you can think of by coupling those two? Thank you.
So basically, you can also fabricate microresonator from silica optical fiber that we have in the lab. You can use that. During my time, I fabricate the spherical resonator. This manual splicing. Nowadays we have this auto splicing in our lab. Sumitomo, everything. That's auto splicing. We press the auto and then they splice. All splice splicer again. We can manually we can choose to splice them manually. Now to splice the optical fiber manually. By having this manual control, you can actually fabricate microresonator from the tip of your silica optical fiber to reshape the optical fiber to be round. So that's what I did during my PhD time. Reshape the optical fiber using that normal splice, manual splice function on your splicers. So of course, there's a lot of applications you can do as biosensors. You have a liquid base. You can have a chamber. You have a microresonators. You can functionalize the microresonators to observe detections via shifting of the position of the resonance mode. So the similar concept, whatever that we have in fiber-based optical sensor, shifting in the resonance of resonance modes. That's also happened in microresonator, shifting in the resonance modes due to changes of the surrounding materials. Similar concept, different structure. That's it. So whatever that you can achieve in the optical fibers, you can possibly achieve in microresonator by suitable tweaking the structures and so on. So yes, but the tricky part, resonator is very small. It's more challenging. We need microscope and everything to work with them. You might be losing your microresonators. So that's the challenging part of the microresonators. To fabricate them, very easy. I think we have Dr. Narizi here with us today. Dr. Narizi can easily fabricate microresonators, cylindrical shaped microresonators. So yes, if I'm answering your question, yes.
Wait, let me clarify again my question. What I meant was when you couple it with a tapered fiber, right, in the slide, you couple the microresonator with a tapered fiber. So I was wondering, like, are there any applications from that coupling?
Oh, so basically the coupling is just, that's how we inject light into the resonators. So basically the tapered optical fiber that we have there, the function is to couple light inside the resonators. So I'm not sure. So when we're talking about resonators, I think the focus is more on what the resonator can do. I guess if you want to play around with the coupling of tapering parameters to how you can excite plasmonic modes, different plasmonic modes, order of plasmonic modes in the resonators, you can do that. We have papers on that from Dr. Narizi. So by playing around with these optical fibers or tapered fibers that you use, you can excite different modes of your resonator. The same concept in optical fiber, we have fundamental mode, we have higher order modes, we have different modes. The same concept exists in resonator. We have very fundamental modes that travel very close to the surface of microresonators. So if you can really match and excite the fundamental mode in the resonators, you can have even highly interactions from your resonators. So yeah, you can play around with the couplings to excite different modes in your micro resonators. And if you can excite the fundamental modes, you can do more from the resonators. So that's what I can see.
Okay, thank you.
All right, Nadiah sent a smile over there.
All right, we have another question from the chat box. It's from, I think, Dr. Fairuz. Can we manufacture fibers locally with high relay scattering?
So I'm not sure, to be honest, in Malaysia MMU Unit 10 got this drawing power, but I'm not sure how. Um, if we have, I'm not sure about this to answer this relay scattering. Really, I'm not sure whether we can have that one in Malaysia. So, but I saw CVD laying around somewhere in the faculties. But maybe not much people want to venture around CVD. We have chemists, very dedicated chemists. We can, of course, use the CVD technique at the right temperature. We can deposit different types of material inside the core. Even you can use a hollow core fiber, right? Not the fancy photonic crystal, just a very hollow core fiber. You can pump in highly nonlinear liquid inside the core, and then you can have highly nonlinear fibers from that. But of course, you need suitable pump so that we have continuous of liquid, okay, on your structures. That's what I did try. I did try that, but I don't have suitable circulating liquid inside my core, so that I'm not able to achieve anything from that. But yeah, yeah, I think that's that's it.
Okay, we have another question. Is dispersion one of the parameters that affect the duration of output pulse, and how do we calculate it? The goal is to get shorter pulses.
Dispersion is one of the matters that affect the duration of. Okay, when you have optical fibers, yes, the dispersion is going to play a major role in your pulse propagation. Okay, when we are talking about short pulses, is they contain lots of frequency, lots of. This is Fourier transform. Short pulses, broad frequency. So all these frequencies, okay, they travel at different speeds. Whether the blue component travel faster, the red component travel faster. So at normal and anomalous dispersion regime, all these different components travel at different speeds. So there's a match that you need to do in order to calculate these dispersion parameters, dispersion properties inside your optical fibers. My group during my study time, they did calculate the duration, the dispersion properties. Okay, similar to what we have in Selmayr equation, right? We can use the Selmayr equation to get the dispersion profiles, total dispersion profiles. You can also have that in your fibers, so that you can choose which dispersions that you require for your interactions. So that's selecting the dispersion regime where you want to work is important, because all these short pulses have broad frequency regime, and all these frequency travel at different speeds at different dispersions profile. So yes, how to calculate. There are certain equation. Of course, you can use this book. Plenty of equation that you can see from this book. Even I, if you want me to do the simulation for you, I'm also vomiting myself. But yes, you can use all those equations from this book. The goal is to get a shorter pulse. So of course, you can you can shorten the pulse where we call it pulse compression. Okay, pulse compressions. Pulse compressions use balance. That's the importance of balancing your dispersion and nonlinearities. So when you can play around with all these two terms, dispersion and nonlinearities, you can broaden your pulse, you can shorten your pulse, you can slow down your pulse, whatever that you want to do if you have a good platform to do it. So yeah, the answer is you can set, you can you can compress your pulse if you can find a balance between your dispersion and also your linearity. So yeah.
I think there's another question related to this answer. What kind of signal processing you use for the pulse compression, I think?
What use signal processing that I use? The effect that I use is kernel linearity, kernel linear effects, because kernel linear is ultra fast. And my colleague use different. Some of them use cross phase modulation. Some of them use two photon absorptions. So yes, this interaction can give you all optical signal processing. So yeah, you
Okay,
can
so I
use.
think we're going to take one more question. This is from Dr. Saiful. Salam, in normal practice, how narrow the duration of pulse is required for generating a supercontinuum?
So, hmm, so I always work with femtosecond back then. Uh, the repetition rate also play a role when we are talking about pulse lasers, right? Average peak, average power, pulse duration, repetition rate. That's the three most important things that you need to control to get high peak powers. So femtosecond, picosecond, yes, that's the time regime preferable, but it's very expensive lasers. So if we can make sure that we can have repetition rate, uh, faster repetition rate and faster lower repetition rate, so that you can control the peak powers from your lasers, you will for sure generating your supercontinuum, balancing the dispersion and nonlinearities. That's why when you wanted to do the dispersion, the nonlinear experiments, it's very important for to characterize the properties of your fiber first, so that you know these properties. That what I did when you have that nonlinear fiber, characterize the nonlinear parameters, characterize the dispersion profile, so you know where you should go. And then once you have that, you can use suitable pulse lasers to be injected into your core. And then of course, pulse lasers are very expensive, millions. I'm not sure whether we in Malaysia are going to one day have a nonlinear lab in Malaysia, nonlinear optic lab, but maybe one day my lab ke kan kot lah aku nak collaborate dengan nonlinear optics, so who knows, right? Yep, that's all.
Okay, thank you very much, Dr. Fariza. I think before we end our session, I'm not going to take any more questions. I would like for everyone to turn on their video, what do you call this, video cam. Turn on your videos so that we can take a picture together. Is that okay?
Terima kasih datang dengar. I'm just struggle lecturers too.
Okay, so this is the amount of people that we have. Okay, so I'm just gonna take a screenshot kejap Okay, 1, 2. Okay, kejap. 1, 2. 1, 2, smile. Okay, that's it. Thank you so much everyone for coming. I hope to see you in the next photonic lecture
Thank you
series.
very much.
Thank you.
Bye-bye.
Assalamualaikum semua. Bye.
Thank you.
Okay, bye.
Salam.